All right, recording is rolling. It is Tuesday, November 14th. Our main focus today is going to be these chapter 6 puzzles from your textbook. We did about half of them the other day, so we're going to do the other half today. Well, we'll get pretty close to doing right to finish this. Try these in just before you leave for the break. So you finish these by tomorrow. That's good. Takes us till Friday. Uh, you guys' energy quizzes came back to you yesterday. If you don't have it for some reason, it's probably in your folder in the back. Uh, oh, some other things because we're going to the Thanksgiving break. So give you guys a little checklist here. Things to make sure you have turned in. You guys remember this momentum half page? Right, we did this all in class. So this is like an additional homework I'm treating this as. A lot of you guys already turned this in. If you haven't, then get this in again before Thanksgiving break. Then I'll get the points of the book. We are coming up against the end of an interim. So technically tomorrow is the last day of sort of interim period. And I think the last grade that's going to go in there is going to be, well, I have a couple things lined up for you guys tomorrow. So it's always kind of a tight fit with AP. There's so much stuff we do. There's a collisions lab I want to do that involves like bouncy balls. I also want to do an FRQ. So one or both of those might end up being the last grades there. Right? And then just get all those stuff in by, well, before Thanksgiving break and be all good. All right. Oh, your momentum take-home quiz. All right, I have that right here. So I finished writing this last night. I printed them up this morning. I'll give this to you guys the last minute of class today. All right now, this take-home quiz. If you want to finish this in the next few days, so you don't have to think about it over Thanksgiving, then you'll have a few days opportunity to do that. So that's a good amount of time, right? Right. If you want some more time to think about it, here, I'll give you guys, let's have this just do after Thanksgiving break. Right? So if you want a good solid like week and a half to think about this and work on these problems and really think deeply on, you have that. Right? And then we're still doing the in-class quiz on Friday. Now, this in-class quiz won't be as difficult as the AP quizzes that I normally give you guys because this is geared towards, well, all kinds of physics students in all different physics classes. But I told you guys about that. So Friday, when you guys walk in class, all the desks will be in rows. And I'll give you guys an in-class quiz that covers both energy and momentum, right? Remember, it's both energy and momentum. So a couple sections there. Yeah, so I got this within reach. What might be helpful is you guys remember all these thumbnail notes I gave you? Right, all the green banners are energy related. All the blue banners are momentum impulse related. All right, so there's where we are in the class. So let's look at chapter 6 puzzles. Yep. No, I'm gonna take these down. I think Thursday evening. Yeah. So, but yeah, it's okay. So this quiz is gonna be like if there's something fundamental, I think you should like obviously be able to get like, okay, well, potential energy is MGH. I mean, like how many times have you done that in class, right? Okay, you should be able to get something like that. If there's something a bit more complicated that I want you to be able to navigate, then I'll list out the formula, right? So, it's pretty ready to go, but it's something that like so any level student, any level physics student should be able to handle something for this section. All right. So where we left off on this was, I think 19 we had set up and started to solve, but we never actually finished this out. So I'll go back to the beginning and solve this one. You might have a start on this in your notes, right? Okay. So we got here the front of a 1.2 meter, or sorry, the front 1.2 meters of a 1,400 kilogram car designed as a crumple zone to collapse to absorb the shock of a collision. Car traveling 25 meters per second, stops uniformly 1.2 meters. How long does the collision last? What's the magnitude of the average force on the car? What's the acceleration of the car? Expressed acceleration is a multiple of acceleration due to gravity. Right. So let's get this drawn out, get a picture going. Right. So yeah. Classic car shape right here. Right. Got some wheels on it. Right. And let's say we're doing like a crash dummy test. So we're sitting in this car with some initial velocity, about like V naught. Right? Initial velocity is going to bam, it's going to crash into that wall. Right? It's going to come to a stop and ooh, this crumple zone distance right here. Right? So here's your, well, I'll just call it X, right? Like the displacement is stopping. Right? Now there's like one word in here that's doing a lot of heavy lifting. It has to do with how this collision plays out. You guys see the word uniformly? It stops uniformly. Right? It's kind of taken for granted in this class that something speeds up or slows down, it's going to do that at a constant rate, like acceleration would be constant. But that's really critically important for this crash test. If you guys are ever designing cars one day and you want to like maximize the safety, right? Here's why. If this car was like so, what if this car was like so rigid, it's like made out of steel, like nothing can been this car, it goes like, doesn't just like stop all at once. In which case, this delta x or this x would be very, very small. And that would be bad for you as a driver. Let's throw a little test car dummy in here, right? That would be bad, right? Why would that be bad? Well, let's think about this expression, right? So impulse delta p, you could get it from average force for some time interval, and that's going to result in some mass times change in velocity of the car, right? You could take this delta t, this time interval, divide that over, and that looks like average force is equal to mass times delta v over delta t. Hey guys, what is delta v over delta t? Acceleration. F equals ma. Oh, we're back to Newton's second law of motion. Yeah, you guys remember this, right? Here's the impulse setup. Here's Newton's second law of motion. They're next door neighbors, right? Some physics teachers, they say they're basically the same thing, right? Right. So if you take this delta x and make it really, really tiny, okay, well, it doesn't directly show up here, but also delta t, the time interval, would also be really, the time interval of coming to a stop would be really, really tiny if the car was completely rigid and didn't crunch at all. So this delta t is getting very, very small, right? So what is that else? That affects some kind of balance in this equation. What does it change, right? Well, the mass of the car or the mass of you, right? The masses are changing. That's some value, right? The delta v also doesn't change. The change in velocity doesn't change. Here's what I mean. The car's going at some initial speed and it goes to 0. It's come to a crash stop. So whatever that difference is, it doesn't change regardless of how the car comes to a stop, right? So that doesn't change, that doesn't change. So if delta t is getting very tiny, that means the average force is getting very what? Very large, right? Anytime you see two variables multiplied together on the same side of an equation, they have an inverse relationship with each other. One gets small, the other gets big, right? Like you could have 4 times 6 is 24, or you could have 1 times 24 is 24, right? One gets smaller. Okay, so right. And what about the flip side? What if your car, instead of made out of like steel that could never bend at all, what if it's made out of cardboard? It's like, right? That like completely collapses with like, doesn't get any resistance at all, right? Well, that means that the car like wouldn't be slowed down, wouldn't be slowed down, so that by the time it does slow down, that also happens all at once, and you run into the exact same problem, the exact same numbers, right? So to maximize the safety of the car, you really want to minimize this average force on the car, and the only way to do that, because you can't affect anything on the right side of this equation. So you have to increase the time of that collision, right? And the way to do that is you want it to slow down uniformly, right? So you make it out of material so that it does crunch, but it does so at a uniform rate, right? So it slows down crunch, right? So that's like some of those little details that are kind of behind the scenes that are you always want to consider with this, right? I know textbook problems, of course, they give you a bunch of numbers and somebody can solve it, which we're going to do anyway. But think about all those little implications too. Right? Now, as I was solving this earlier today, I actually saw these questions, I think, backwards in the order that they asked them, because I was looking at this saying, was the first question A was how long does the collision ask, like a time interval, right? And from this point of view, well, can't quite get there, but that's really, I think, a kinematic question, right? Because if you make a tax VB table, like a checklist, let's say what it would be like way back in the day. You guys remember this kinematic checklist, right? There are 3 kinematic values here, so you can solve everything going on kinematic, right? And we'll worry about the forces and the everything else like. Right? So they told you 1.2. Here, maybe I'll just use their numbers on this one. How about that? Use their numbers. We want 1.2 meters to come to a stop, right? It slows down uniform. Oh, stop, guys! What does that tell you about final velocity? 0 meters per second, right? They didn't explicitly type that number, but you have to figure that out, right? They said the car was going like 25 meters per second, right? That's about highway speed, by the way. It's about 60 miles an hour or something. Right? That's 3 kinematic values. That means that this is solvable in terms of kinematics. Now I don't know A and I don't know T. So if I start with just one of the, look, it's the 3 amigos. If I just start with one of those, remember I don't know A and I also don't know T. Which one of these can immediately tell me something? And there's only one. The third one, okay. Because the first 2, it's like, okay, well, I don't know 2 things there. I don't know 2 things there. You could do some crazy system equation, but you're right. Yeah, let's just do the third one. Let's just jump straight to that guy. So I'm going to go final velocity squared equals initial velocity squared plus 2ax. Right. Just going to rest. Right. You guys can stay a step ahead of me. That's a good idea. Right. This part, what we're just a little plug and chug right here. And we can solve for acceleration. because we know everything else in that setup. Right? So I think I'm going to square this, subtract it over, and then divide by the 2 and the 1.2 meter. Okay? So acceleration is, here. In terms of variables, it's always a good idea to keep an eye on variables, right? Would it be negative initial velocity squared divided by 2x is what it comes out to be? Right? And with the numbers, it works out to be, let's see, 5 squared divided by 2 times 2. Right. I'm getting, okay, so it's negative, so now 260, and it's, guys, what's the units? It's 260 what? Meters per second squared. Yeah, because that's the rate that it's slowing down. Right? Okay. Which is actually answering question C. Right. So we are actually answering question C first. So what's the acceleration of the car? Right. Oh, and C actually has 2 parts because they also said how many G's does that represent? Guys, how many G's is that? 26. Yeah. Because every 10 meters per second squared is a G. Let's up some railroad tracks in case you want to see the railroad tracks. I can say the acceleration is, I've got 260, well, maybe we'll do the magnitude of the acceleration, right? 260 meters per second squared. Right? Railroad tracks, every about 10 meters per second squared represents 1 Earth G, right? If you guys are ever, say, like on a roller coaster ride or like in a car speeding up, slowing down, or right, you're in a jet, that's right, you feel the G's, right? How many, right? So it's like 26 G's. So during the crash, you feel like 26 times as heavy as you normally do. Right? Now, it only asks for a tiny time interval. That only lasts for a tiny time interval. All right, what else they ask? How long does the collision? Oh, how long does the collision last? That is the other kinematic variable that we also could have solved for. So, which one's the easiest one to navigate to get the time period? Yeah, I like the second one also. Right. First one almost looks quadratic. I think you could actually get around by factoring out a t. Yeah, let's just do the second one. Okay. So final velocity equals initial velocity plus at. Okay. We're going to rest, of course, from this many meters per second the car was going. We know now it's slowing down at this rate, so it's negative. It's great, right? So how much time? Right? Good idea too. Always think like what would be reasonable numbers to come out of something like this, right? Maybe even before you go plug in and check it, right? You got a car crash. What's the time of the collision? Do you guys think it may be a tiny fraction of a second, right? So I hope the number on my screen is going to be consistent with that. See, subtract over 25, divide by 260, the negatives cancel out. I'm getting, oh yeah, look at there. The time of that collision, maybe we can call it delta t, you do delta t, right? The time of the collision is 0.096 seconds, right? That's, if I round it up a tiny bit, that's like a 1/10 of a second. Yeah, that looks reasonable, right? The car came to a stop and it took a 1/10 of a second to do that, right? You might remember from the roller dropping spectrum. You guys remember like dropping rulers, right? Your friends would catch them, right? Do you guys remember what the average human reaction time was? It's about 0.2 seconds, which is like, ooh, like twice this. Huh, right? I guess, yeah. Okay. Right, and that was a question A, right? Was the time of that collision? Maybe I'll call it delta t, right? Like time of that question. Question B, what is the magnitude of the average force? Average force, right? This is a collision, so my first thought was something to do with impulse, right? But you know what? The way we approach this through kinematic, I think I'm just going to go through Newton's second law of motion, is what we do, right? F equals ma. Right? Can we just do F equals ma? Call this close. All right, so question B, F. Right? This is really an average net force, is what this is, right? Equals ma. Right? And it would be a constant force if we assume it slows down uniformly or something. Right? So we got mass of the car was given as this many kilogram. And we figured out the acceleration was this many meter per second squared. Put it all together. And looking at this many, it's negative, right? What's the unit? Newtons. Hey, could I call that like this many kilonewtons? You like? Right, so I think either one of those work for the force in the car. Okay. Negative tells you the direction, it's backwards, so down. All right, all good. Blah, 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 blah. Sorry. Oh, let's do one more thing with this. I mean, there's always little side questions we could go on this. See if you guys get the fundamental premise of our assumptions going into this. Suppose you made a force versus time graph for the collision. Okay, let's say the collision starts right here. Right, what does that graph look like? What does that graph look like? Can you guys draw that graph? What does that graph look like? Because while you guys are thinking of that, trying to give you guys a head start. If you guys get the correct answer before I draw it, then it's good sign, right? Right. Now remember, for a lot of these impulse graphs, I told you to look for like triangle-shaped graphs, and I walked through that story, right? You make contact, and the force builds up, and maybe rebounds, something like that, right? But I think for this one, I would not draw it that way. I'm going to put 0.1 second here. I'll just round to 0.1 seconds, right? Times in seconds, right? Force, let's call this like kilonewtons, right? This could go up to 364. Maybe I'll just do magnitude of the force. Right? I'm going to draw. Did you guys? How many guys drew a flat graph just like that? Flat graph just like that, right? Right. Because we're assuming a constant force, so that it slows down at a constant rate. Hence the word uniform in uniform acceleration. Stops uniformly. That word right there, uniformly, tells you that that graph looks just like that. All right, are we good? All right. Now there are a bunch of questions here I did not circle, but I mean, if you guys are really curious, ambitious, and want to get the most out of this class, then always feel free to look at some of these other ones. I do want to mention a couple of these. Like number 23 and 24 are the same question, but one's with the numbers and one's with variables. And I want to point this out because I've seen AP ask similar questions to this one. Now, this one takes some deep thinking. Of course, all the solutions are posted so you can find this, right? It involves a girl standing on a plank. The plank is on a frozen lake. Okay, so frozen lake in a physics textbook, that means no friction, right? And she's like walking along this plank. And the question is like, what's her velocity relative to like the ice versus the plank, right? Got a bunch of relative velocities going on. So I at least want to draw this out just to find some ideas. How do you guys think about this? Because I've seen AP ask similar type questions. Suppose you're standing on a plank. And yeah, maybe it's on a frozen ice pond, right? Or AP's version of this is sometimes the plank is like floating in water. You have like floating in water, right? And similar idea is that if you assume there's no drag force in water, again, simplification, right? Then if you're standing on this plank, as you walk to the right, guess which way the plank is going relative to like a nearby dock? It's going to go to the left, right? Right. And AP's version of this, if you ever see an AP question, well, okay, good chance you're going to get a question pretty similar to what I'm trying to get right here, right? Is what if you look at the center of mass of the solar system? Suppose you start off like standing at the center of mass of the board. So the center of mass of you plus the board as a closed system could be like at some location, right? And you walk to the right. Well, the center mass of the plank is going to move to the left, but the center mass of the entire system, you plus the plank, guess where the center mass stays the entire time? Right where it started in the beginning, right? As long as it's a closed system, there's no drag force from the water, blah, 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 right? Right? If you and the plank have equal mass, then you move equal distances relative to the nearby dock, right? If you have a greater mass, then you're really pushing the plank a long way. If you have a tiny mass compared to the plank, maybe the plank hardly moves. And the other one I want to point out they did not assign to you is, involves these shuffleboard discs, which I actually have a poster for right now. My honor students actually did walk through a question like this, but AP, I've never seen them ask this question, so just look at this, right? So actually, basically, this right here could answer, or it could be the setup for this, right? You guys see a shuffleboard, pow, just like that. The honors question, they have an identical looking setup with billiard balls. It looks like pretty much exactly like this picture too. Right? So, and you could run this in reverse too. There could be like a car collision, right to left, to right, right. Either way, right to left, left to right, right. The momentum is going to be conserved along each axis because this is a vector value. So you say, in this case, maybe there's a shuffleboard or billiard ball moving to the right. Right? That's applying all the momentum strictly in the x direction. So you could split this into components. Say the components have to add up to the original momentum. Right? And in the y direction, well, there was no momentum to start off at all. This was zero because there was nothing moving up or down. Therefore, after the collision, bang, however much this one's moving up, mass times velocity, this component up, is mass times velocity, this component down, so that it zeroes out. Right? That's how you use that. All right, so I just want to mention those. How do you guys think about those a little bit? If you want to give yourself a challenge, go try to solve it. Right, next one I have circled though is number 42. We got a so many kilogram car moving this speed, pow, collision with this van that was going slow in front of it. It's a little fender bender situation, and they kind of bounce off each other. And the question is, how fast does that van take off? And then the follow-up question is, how much mechanical energy is lost, okay? Which you can check by kinetic energy. Okay? So let's all that together. Got number 42. Okay. So car, mass car. They said 1,200 kilograms. What if I change these numbers a little bit? Let's go 1,100 kilograms. Right. I won't change them crazy much, but let's say speed of the car. Let's just say velocity of the car. At 25 meters per second. What if we make that like 26 meters per second? Right. And then it's gonna run to this van. Right. Mass of the van. Have that was a really heavy truck. Let's call it this many kilograms. How about that? Okay. And let's say it was initially going at velocity of the van is trying to get numbers that are kind of similar to theirs, but not crazy different. Okay. How about 21 meters per second? How about that? Okay. So pow, collision, right? Kind of right? And then post collision. Okay, so this is all initial. So initial. Okay. I'll say velocity, car, final. Say it slows way down to like 20 meters per second. Right. And then velocity van final is, all right, well, that's the question. Okay. That was the first question. How fast the van going? Okay. It's got like a before and after. Okay. So this is like before collision. Right. And here's some after numbers. Of course, the mass will stay the same. So well, collision. Open a physics textbook, you see a collision, think, oh, conservation of momentum. Right, that's how I'm going to solve this. So the first thing I would jot down is this right here. If this was an AP FRQ, that might be a point by itself. If you just jot that, supposed to, so you got 20 seconds to put down your pencil on the test, and it's like, now it's time. Right? Well, I can just jot that down. I might take up a point. Right? Right. Now let's put in all the little bits. Mass, car, velocity, car, initial, plus mass, van, velocity, van, initial, equals mass, car, velocity, car, final, plus mass, van, velocity, van, final. Boom. Right? That's just general conservation of momentum. I think that matches. Yeah, that's just this right here. Right? Even a little simpler because no reversal of directions. I have positives and negative velocities, but here it's just all positive velocities. Okay. I think this one's pretty plug and chug, isn't it? Let's do some plug and chug. See if you guys can beat me to the answer here. Kilogram, meter per second, kilogram, meter per second, kilogram, meter per second, kilogram, meter per second. All right, and what's my numbers? Remember, my numbers are a little bit different than your numbers. So that mass of the car, there and there. Mass of the van, there and there. Velocities, initial, and then van initial was like this. Okay. Then car, okay, then post collision, the car slowed way down to this number. So what's going on with the van? Call it V van final. Okay, good software. Okay. So very plug and chug. I'm just gonna add all this up. I'm gonna subtract this out, and then divide by this mass. That's it. You guys have probably done that so much. I think you guys can all get it from there. So here, I'll just do this while you guys are wrapping up whatever on your paper. So that mass times that velocity plus that mass times that velocity minus this mv equals, right, and then divide by mass of the van. I'll tell you the velocity left to the van. So velocity van final is, I'm looking at 21.94 meter per second. I'm keeping a lot of digits there because, right. Does that look reasonable? Yeah, the van speeded up a little bit, which would make sense, right? This little bump, right? And the car is not overriding the van, right? So sometimes with these momentum setups, you can create something that's like physically impossible, like ghost cars that go through each other, or if you're not careful, right? Or another thing to keep your eye on is kinetic energy, right? Because I just made up some numbers on the fly. Careful with that though, because sometimes like you can never have something where the car runs to the van and then like the kinetic energy ends up increasing. Like the van can't take off like a rocket or something, right? Oh, you can make the numbers come out like that, but right. Let's check part B. What is the change in kinetic energy? Okay. So part B, because that was part A. Yeah, you should.
The numbers.
Huh?
You change the numbers.
Okay, yeah, there should be less kinetic energy after them before, right? Okay, okay. Yeah, so you should get a loss in kinetic energy. Let's say, what is the sum of kinetic energy initial? And what is the sum of kinetic energy final? Because delta K would be K final minus K initial, well, the sum of, right? Got two different corresponding, right? Okay, so I'll do 1/2 mv squared for car plus 1/2 mv squared for the van. Initial, okay. And then final I'll do 1/2 mv squared car final plus 1/2 mv squared van final. Something like that, right? Just plug in the numbers they got. Right? Now most of these were given. The one we solved for, the speed of van post collision, is going to pop in right there. Okay. So we get got all my numbers on the other side. Let's do 1/2 mass of the car times initial speed of the car squared plus 1/2 mass of the van, initial speed of the van squared, right? And I'm getting a big old number. So, okay. So sum of kinetic energy initial is, I'm getting 1.9 million joules. Okay. So sum of kinetic energy final. If I create something kind of realistic, then this number should be less than this. It could possibly be the same if it's perfectly elastic. Small chance of that happening. So see 1/2 mv squared is post collision. So 1/2 m of the car times v post collision squared plus 1/2 mass of the van times this post collision velocity, which we solved for. So I kept some extra digits so I could save a rounding for the nth square. Right, I'm getting so it did go down, but only a tiny bit. 4.773 joules, something like that. Yeah. Okay, so I just made up some numbers on the fly. This does work. Right? This could be realistic. But my collision, just looking at the numbers, guys, is my collision extremely inelastic or extremely elastic? Look at my final kinetic energy compared to my initial. Let me take a ratio. 191. I've got 99.5% of the kinetic energy was conserved. This is extremely elastic. This is extremely bouncy, right? It's not perfectly, but it's pretty dang close. Yeah. And then for you guys, probably something a little different. Hey, you guys got that? I think that's a pretty plug and chug kind of question, right? Let's do number 56. Ooh, okay, now this one's a little more complex. Takes a little more thinking, right? Got bullet mass m, speed v, passes through a pendulum bob, mass capital M. The bullet emerges with speed v over 2. Interesting, right? Now, you can see from this diagram, already start to put this together in my mind, this looks kind of ballistic pendulum, right? Like if you fire a bullet into a block. Now, the way I think you explained this before is like the bullet embeds in the pendulum, but here, this is kind of an alternate version of that because it passes through, right? The pendulum bob is suspended by a stiff rod of length L and negligible mass. What minimum value V, the firing speed of the bullet, so the bob will barely swing through a complete vertical circle, right? There's little details in here that change the answer a lot. Like, you guys see this where it says stiff rod? You guys see a stiff rod of negligible mass? What if they made that a string of negligible mass? Would that change the answer? Yes, it would, because I remember to go in a complete circle with a string, you guys remember it has to go at least the square root GR at the top, right? We figured out that for centripetal force, blah, 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 right? Yeah, it would have a minimum speed of GR, or sorry, square root of GR. If it was going any slower than that, it would make the circle the following. But a stiff rod, A stiff rod would have minimum speed of like 0 meters per second at the top. And as long as it was going at least that fast, then you just barely make it around. Okay. So it's a little bit simpler than a string. A little bit simpler than a string. Okay. Oh, where is? Let's see if I can dig up my poster on. Here's my poster on ballistic pendulum. Now this isn't exactly that, but it has a lot of commonalities, right? My version, the bullet embeds in the block. That's inelastic. Right? They have the bullet passing through. It's kind of an alternate version. Right? And I have it swinging up like some height change. And for the one we have, the height change is gonna be like the diameter of a circle, isn't it? And wouldn't that be like 2L? Like if this swung up all the way to the, like make it a circle, squeeze off the page, that would be like 2L, right? You see that? Right? Which is what we have right here. So I was trying to kind of modify that version I gave you, right? Now they did ask the firing speed of the bullet, which is also kind of what the setup for, right? And remember how I told you to solve this and what we're about to do, right? Is chronologically the bullet fires through the block, and then after that the block swings up to some height, right? But the way we solve it is in reverse order of what happened. So we're going to start with the end product. That okay, well it swung up to some height, and then say, well, what collision got it going in the first place, and then therefore what speed of the bullet would have set everything into motion to start with, right? So we're going to solve in a reverse chronological order, right? Same on the poster as what we're about to do right here. Okay. So to swing up to some height, I'm going to start with conservation of energy. Say it had to swing up to some height. So I'll take care of the energy part first. That's like this green box sort of I'm thinking of, right? Vector. So sum of energy initial equals sum of energy final. Okay. Let's see if you guys are keeping close track. Right? Like why did I write that and what would feed into that? I've set up a closed system. I'm saying energy is conserved. Guys, this is a closed system of what and what? Right. What is in this closed system? The block and the earth, right? The bullets already passed through the block. We're done with the bullet. We're saying that's happened in the past. I'm going to say there's some 1/2 mv post collision squared for the block. That's the mass of the block. That's the capital M mass of the block, right? And it's going to send it up to some height, right? I'll call it mgh, right? And that h is 2 times the length of the rod, right? That's a stiff, negligible mass rod, right? That's like the height change, isn't it? Right. And that's it. That's the entire conservation of energy setup. Remember, I don't have to say plus in any kinetic energy because it's not a string, it's a stiff rod, so it could go up to well, like minimum like 0 speed at the top. Right? That's why I gave it no kinetic energy at point B. Right? We went from point A to point B. Right? Point A is right after the collisions happen, after the bullets pass through the block, it's getting the block set in motion with this much kinetic energy, and all goes to potential energy at the top. Right? Now so this is the here, I'll spell it out. This is the block. Wait, do they call it a block? Oh, no, a bob. A bob. Okay, we're calling it a bob. The bob Earth system. Right. Notice I'm not considering the bullet. It's part of something else. Right. The mass cancels out. Cross multiply by 2. Take the square root. So the speed that had to be going to get up there in the first place is okay, square root of 2g2l, right? It's like square root 2gh, isn't it? Square root 2gh. Times you guys seen that. This 2 and this 2 combine. Bring that out. B post is 2 times the square root of gl, right? Did they give us numbers? Oh, no, they did not give us numbers. All right, solve variables. Okay, well, that's all right. We'll do that. Right. So this is the speed that you would need so that it is able to at least swing all the way to the top of the circle and therefore continue in a circle. Right. That's the first half. Right. Now we're going to switch over and think, well, what firing speed of the bullet would have let it achieve that post collision velocity in the first place so that it could get up there. Right. That's going to be collision physics. We're going conservation of momentum. Sum of momentum before the collision equals sum of momentum like, post collision, initial final. So we're switching gears here, okay? And the bullet is supplying all of the momentum. So here's the mass of the bullet times the firing speed of the bullet. And the ultimate question is, what is the firing speed of the bullet? Right, so this is bullet, right? Bullet. Right? And it's going to go to, well, the bullet passes through the block and it gives the block some speed. So it's 2 separate masses, right? The bullet and the block are doing two separate things, right? The bullet goes on, mass bullet, with half of its original speed, they said, that's v/2. And whatever momentum was left went into the block. So that's mass of the block, right, times the post-collision velocity of the block, the post-collision. Right? And how fast does it have to go? Well, it's got to go so fast it can go all the way to the top. How fast is that? Oh, well, we just solved that. That's that right there. That expression is that. Right? I say too? Okay. So looks like all I have to do is divide by the mass of the bullet, and I pretty much have the answer, right? So the speed, the firing speed of the bullet to set solid motion is. Right? Oh, wait. Never mind. Let me subtract this term over. Oops. Because this is the same variable, isn't it? Oops. Right. So let me subtract that over. Right. So 1/2 mass bullet, velocity bullet, or so something minus half of itself is half of itself, right? Got mass block times, and I'll go ahead and make the substitution right here. Right, 2 times the square root GL. You like that, right? Okay. All right, so we still got one more step. I ran out of paper. It's all right. Okay. I got to cross multiply this 2 and divide bound by the mass of the bullet. So V bullet is, okay, 2 and 2, that'd be 4. I got the mass of the block here. I got a square root GL, and I have to divide by the mass of the bullet. Okay. I think that should be the answer, right? That'll look right, I think. So, okay. A good thing to do when you get an answer, maybe in terms of variables like this, is run through and say, do all the proportional relationships kind of make sense? Like, for example, let's go through them one by one. Right? What would have to happen to the firing speed of the bullet if, right, and we've got 4 variables on the right side, if the mass of the block increased? Let's say we replace one block with a heavier block. Do you have to fire faster or slower? Faster, because it's a direct relationship. In fact, if you have 3 times the mass of the, or this is the Bob they were calling it, oops, not block Bob, or block Bob, right? Bob, right? If it's 3 times the mass of the Bob, it would be 3 times the mass, the speed of the bullet you have to fire. Okay? What if the bullet itself was more massive? If the bullet's more massive, you don't have to fire as fast. You guys see that? Right? Okay. Kind of makes sense. If you fire like a cannonball, you don't have to fire as fast, right? It's got a ton of momentum. If the gravity field of the planet increases, you have to fire faster. And if the rod was longer, it will be a bigger circle. You'd also have to fire faster. That's those close square root relationships. All right, number 75. Measuring the speed of a bullet. Oh, we got another bullet. All right. A bullet mass M fired horizontally into a wooden block, mass big M, because we got little m and big M. Right? Lying on a table, the bullet remains in the block. Ooh. Right, so inelastic collision. It kind of makes me think more of this type setup. Okay. The coefficient of friction is mu, and the block slides some distance d for it come to a stop. Find the initial speed of the bullet in terms of variables. Oh, so another solve in terms of variables. All right, these are fun. Let's get a picture and figure this whole thing out. 75. Got table surface, block, mass big M. The bullet was fired, or so mass called little m, since fired at some speed. Maybe we'll call it V bullet, some velocity, right? And then it's going to embed in the block, and this whole thing's going to, on the surface with some coefficient of friction mu, maybe a mu sub k, coefficient of kinetic friction. It's going to slide some distance d before it comes to a stop, right? Okay, so how fast did the bullet have to be fired in the first place? Right? That actually is also the same thought process as this, only instead of, because there's some initial collision that happens, it sets everything in motion. Now, my ballistic pendulum, it swings up some height. We said, well, there's some conservation of energy that can tell you how high it swings. And maybe the premise here is you know how high it swings, so you can back calculate blah, blah, blah. Now here, it's a collision, conservation of momentum, followed by slides a certain distance. And that reminds me of car braking to a stop. And back in the day, we used an open system like conservation of energy to solve, well, I guess work energy theorem, right? Or you could go through acceleration and kinematic, blah, blah, blah. It's a little bit longer process. You could do that with too. Right? I'm going to do the energy process. Right? I guess we could solve this forward in time or backward in time. Maybe we'll solve this backward in time, right? Let's say it goes some distance t. Right? So let's start with the energy. Now, if this is an open system, right, let's get a free body diagram on this block as it starts. Let's say the collision's already happened and the block's starting to slide. Okay. Can you guys draw a free body diagram on this block? What are the forces on that block? Does it have a weight, mg? Does it have a normal force, which is equivalent to the weight, so there's no net vertical force? Right? And then is there a friction force this way, S sub FR? Right? And I try to make this kind of realistic. See how I drew that friction force approximately half of the normal force? That tells you what about the coefficient of friction? Be like 1/2, right? Isn't coefficient of friction just that magnitude divided by that magnitude? Okay. So whatever that would be. Make it some kind of realistic. All right, so let's do sum of energy initial minus work done by friction equals sum of energy final. Let's do a system of only the block. No, let me change it a little bit. Right, block and the bullet that's embedded in it, because the bullet's embedded in the block, so they're all one giant thing. Okay. So remember, the collision's already happened. We're solving this like reverse chronological, right? The collision's already happened. The block is already in motion. That's what kind of energy? Kinetic, 1/2 mv squared. And I'm going to say the block plus the bullet at v post collision, so post collision velocity squared, okay, minus work done by friction. Now, isn't that friction force times stopping distance, right? And when the block comes to a stop, how much mechanical energy? Zero joules, right? It's stop. There's no kinetic, right? It also hasn't gone up any hills, right? All right, so I don't know if this is right. I'm gonna make a substitution here. Friction force. Isn't friction force? Write this down. How about blue ink? Isn't friction force coefficient of friction times the normal force, right? If it's kinetic friction, we're talking about kinetic friction, right? And the normal force is just equal to the weight, same magnitude. So that can substitute in there. I'm going to substitute that in right here. So let's go 1/2 block plus bullet v post collision squared minus, okay, and then make big old substitution for this friction force. This coefficient of friction times normal force, but the normal force is equivalent to, all right, let me edit this. I'm going to backtrack a little bit. Backtrack. Right, this is the bullet plus the block. Oops. Right, so this is like, and plus it's a tiny difference, but you should something cancels out. Oops. Edit my work here. Oops. This bullet plus block is embedded together. So right here, I get a bullet plus block plus bullet, right? G, right? And then stopping distance goes to 0. Okay. What I'm trying to get at is this idea that the mass cancels out, which should look familiar because remember, car bringing to a stop. What's the stopping distance based on initial speed? Well, it has nothing to do with the mass of the car, and we're seeing the same story right here. Okay. So I'm going to solve for this post-collision velocity. Okay. So add this over times 2 square root. Cut through a couple algebra steps. V post-collision is, okay, I'm going to multiply this, so add this over times 2. So that's 2 mu g d, and then finally take the square root. Okay. Now that's not the final answer yet, because the question was, what's the firing speed of the bullet? That's our halfway step. That's after the collisions happen. It gets going that fast so that it goes to stop in that distance on that surface. But we still got to do the first half of this problem, right, chronologically, which is to say, how fast was the bullet fired in the first place? Right, and that's a collision question. Sum of momentum before the collision equals sum of momentum after the collision. Okay? And the bullet was providing all of the momentum, mass times velocity, initial of the bullet, which is the actual question. It goes to block plus bullet. This is inelastic collision, right? Times v post, which is the same thing as square root 2 mu g d. Right. Finally, divide by the mass of the bullet. Velocity of bullet is sum of masses divided by mass of the bullet, square root 2 mu GD. Right? Does this make sense? Well, the more massive the block, the faster you'd have to fire the bullet to get it to slide. Right? Some distance, blah, 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 right? The more massive the bullet, now this one's a little trickier to think about, but if you think about it, the more massive the bullet, the less fast you have to fire it. Right? This, if you make the bullet heavier, like more and more massive compared to the block, this ratio approaches 1. But it would be approaching, like getting smaller and smaller and smaller, which would make the necessary firing speed smaller. Right? So think about that. Right. Let's do. Here, I want to show you the setup for number 76. Number 76 says squid jumps out of the water. Right. It's got a squid. Right. Jumps up. Mass of the squid jumps up by firing water straight down. Right. So we got mass of the water fired straight down. Okay. I can do conservation of momentum. Sum of momentum before equals sum of momentum after. There was 0 momentum in the system, kilogram meter per second. Okay. Got mass of squid, velocity squid up, equal, plus mass of water, velocity of water down. They tell you 3 of these 4 values, and you got to solve for what is the velocity of squid. You can do that, right? You solve for velocity of squid. After that, they say, how high does the squid go? And you set up conservation of energy. Sum of energy initial equals sum of energy final. Okay. We got some 1/2 mv squared turns into mg h max. And you solve for h max. It ends up being, well, you can solve that. Okay, you guys got that? That's how you solve that. I get to get you guys this take-home quiz right before you walk out the door. So let me do that right here. So I'm just going to stop the video right there.